Welcome back. This is network models. Let me drag the objectives over here, interconnecting, and this one is 1.1 compare and contrast OSI and TCP/IP models. We're probably going to have to break this one up into two sections. I'm going to try to limit everything to around 20-25 minutes so that you don't get too bored as you try to watch these things. But we're going to have two models that we use. One's the OSI, the Open Systems Interconnect. The other one's the TCP/IP model, which was originally called the DoD model. It was designed to actually support or to represent, I guess maybe a better term, the TCP/IP networking process. And when we talk about these things, we're talking about how data gets from point A to point B. We have a computer out here which is going to connect to our stack, either be the OSI or the TCP/IP, and then it's going to get transported across the network, and we'll talk about these things in a minute, and get to the other end and connect to a computer. So the computer is not part of this thing. This is the way that data gets sent from point A to point B. Computer, not really. It is, but it isn't involved in it. We'll talk about that here in just a second. But anyhow, why use models? In the bullet points here, reduces complexity of large problems to 7 smaller ones. Instead of, okay, the network's not working, oh golly, where do I start? What part of the network isn't working? Is IP the problem? Maybe we have an access control list that's preventing certain devices to get to somewhere. Can I get to it using the IP address but not the name? What services aren't available? So allows us to look at the issue and determine what's not working. And when we determine what's not working, then we have a better idea of where to start troubleshooting the network. Allows for the standardization of interfaces among devices. In the early days, and some of you may remember this, if you wanted to add something to a computer, you had to go to that manufacturer. If I wanted to put a NIC in and I had a Dell, I had to go get a Dell. If I had a compact, I had to go get a compact. If I had an AST, I had to go get an AST card. So what the models allows is for multiple vendors to produce devices that are standardized, that are going to work on our devices, on our machines, so that we can add capability without having to go back to the vendor. Prevents changes in one layer from affecting other layers, and we're seeing that go on right now as we go from IPv4 to IPv6 would be an example of this. One layer to the other, so IPv4, IPv6. The only thing we're changing is, and we're going to get to it here in a little bit, layer 3 of the OSI model, the IP type that we're using there, and the rest of the network, we don't have to go back and change a whole bunch of NICs. We don't have to change our web pages, our browsers, or anything like that. I know they keep getting updated, but not because of this modification. Allows engineers to concentrate on the specific design of functions in each layer so that they can optimize the devices that they're working on. The 4 lower layers of the OSI are mostly concerned with data shipping, and I'm going to have a picture of that here just in a second. So data shipping to get from point A to point B to get the data there. The upper 3 layers with applications, deal with applications running on the end devices, our browsers, for instance, on our computer, and maybe the web server running on the server at the other end in order to do those things. Multi-vendor interoperability to meet the same networking standards. So we have a standard here, and we use what the IBM PC is what we call it, the IBM PC standard, even though they didn't make PCs for very long. The other standard that we look at is going to be the Apple. Apple is all proprietary. If you want an Apple NIC, you go to Apple and get it. If you want an Apple this or an Apple that, in order to do that. If IBM PCs, we can use the devices that are standardized and multiple manufacturers. To me, more competition tends to lower the prices. Computers and networking gear from multiple vendors can work in the same network, and that is true. We could have Cisco and maybe 3Com in here, or any other of a number of manufacturers. The way that we manage the specific piece of hardware is going to be a little different, but they will interoperate. One vendor can write software that implements higher layers, such as the web browser, and another can write software that implements the lower layers. Microsoft has TCP/IP built into the Windows operating system, so we can use either the Microsoft one, obviously, or we can go get Chrome or Firefox in order to do that. The OSI model itself, and then here is the image that represents data shipping and end application. So the mnemonics to remember these things, if you want to go from the top down, all people seem to need data processing, the A and the A and the P and the P and on down. In the early days, I had trouble with that. I'm kind of dense sometimes. But I learned this other one, please do not throw sausage pizza away. And for some reason, I could remember that, maybe because of my fondness for pizza. But from the bottom up, and the layer numbers are from the bottom up. Layer 1, 2, 3, 4, 5, 6, and 7, up to the application layer. The data shipping, the transport layer on down, is what we're going to be concerned with predominantly in the Cisco world, or in the routing world. The upper three layers, as said, these are applications that run on the computers. In this case, the applications are services like an HTTP service, or a FTP, a file transfer service, or mail server, mail service. This is not Microsoft Office. And I realize that Outlook or whatever, Outlook would connect with the mail service, but it would be the program that runs on the computer that connects with the networking service that's going to run at the top end of the layer. So we have applications on the end devices, application, in this case services. Even, I mean, this is one of those that we have a single word that can mean multiple things to us, but applications in our case is going to be services that run. This is another representation of this model, a little bit maybe better idea of what goes where, with physical layer down here, media, the signal, the ones and the zeros, binary transmissions. We're going to turn everything into ones and zeros at the physical layer. The data link layer, it says router and MAC. Router actually is going to be up here, but the MAC address, the media access control address, switches are going to be at this layer. This is where Ethernet is going to be defined, wireless 802.11, a number of other things that are here, frame relay, HDLC, are going to be wide area network protocols. The Ethernet and the 802.11 are going to be local area network protocols. So when we talk about LANs or small areas, yes they are, but they have specific technical definitions. Wide area network goes a long ways. What a wide area network uses a different protocol in order to get from point A to point B. Layer 3 in the networks, where we're going to have routers, our home router, or wireless router that's going to be here. Path determination, how we're going to get from one point to the other. If you get ready to go on a trip, you're probably going to go to Bing Maps or Google Maps in order to find the path. That's what this layer of the model is going to do for us using routers. And these symbols are these are the Cisco symbols for a router. This is the Cisco symbol for a switch. when we get up here. TCP, UDP, SCP, transport layer, end-to-end connections and reliability. We're going to talk about how it establishes those end-to-ends. The two primary protocols that are here are going to be TCP and UDP, which are going to be the topic of the next objective. The session inter-host communication, it establishes the session and it kind of controls which session, because we might have be getting email, going to a web site and doing a download all at the same time. Each of these are going to be a different session. So it does session establishment, and then it's going to control what session gets the most of the bandwidth, the most of the CPU cycles, the most of the resources in the individual session. Presentation layer recognizes data, what kind of a document is it, HTML, JPEG, MP3, those sorts of things, to be sure that it is supported in the device, so that when it presents it to the application layer, it's something that can be used. So HTML, www, HTTP, if we have that enabled, then HTML is something that can be presented. Doc, I think one of the examples here are PDFs. You can configure your browser to open a PDF, or you can download the PDF. A .doc file, typically you're going to have to download it and then open it separately with the Windows program. We won't say application there. That the Word program or an Open Office program that will work with those. So what do each of these layers do? And I've tried to put in each of the slides an image of the OSI model, so it makes a little bit of sense, or you can see where each of these layers that we're talking about are in that particular model. So the physical layer defines the electrical and physical specifications. How are we going to connect to our NIC card, to our computer? And this is where our connection is going to be. So we could have like an RJ45 twisted pair. We could have fiber, or we could have coax, and you're probably not going to see coax anymore. But and the electrical properties that are going to be designed there. What kind of voltages are we going to use? What kind of formatting are we going to use in these things? Defines the relationship between the device and a physical transmission medium. Electrical cable, optical fiber, the things I just said, or an RF radio frequency link. Are we going to use wireless? So we could have wireless in this. This is going to be defined here. The layout of the pins, the voltages, the line impedance, cable specifications, signal timing, similar characteristics for connected devices, the frequency, whether we got a 5 gigahertz or a 2.4 gigahertz, or in today's world both for the wireless devices. What frequencies are we going to use? Responsible for the transmission and reception of unstructured raw data in the physical medium. We're just going to turn it into ones and zeros to send it across the network. Other layers are going to be responsible for structuring that data. The bit rate control is done at the physical layer. May define transmission mode as simplex, half duplex, or full duplex. Simplex is broadcast. So simplex is broadcast, where we just send it. Half duplex means that we can transmit and receive, but we can only do one at a time. So we can transmit from our device and we can receive, we can send and we can get, but we can only do one at a time. To me, that's kind of like, okay, we're connected to this thing and then we go across a one-lane bridge, so that we can transmit, we can go one direction or the other. We can transmit or we can receive, but we can't do both. So we have half duplex in order to do that. Full duplex, interstate highway. We can transmit and receive and do both at the same time. Advantage here, if we have 100 megabit per second port on a switch, it means we have 100 megabits transmit and 100 megabits receive, which effectively becomes a 200 megabit per second device. So we do those things, defines network topologies, a bus, mesh, ring, and we will talk about those separately. Bus we've already talked about. Mesh, everything's connected to everything else, and a ring, it is in fact just a ring that the data is transmitted in a ring. Token ring is the technology that we use for that. Physical layer of the lower layer equipment such as hubs. Hopefully we don't have those. Cabling and repeaters. Instead of hub, we want to see switch in here. Cabling and repeaters. What a repeater does, let me get rid of some of this mess that I've made here. What a repeater does, when we put a signal on a piece of copper or into a fiber even, it's going to degrade as it goes across the network. We have electromagnetic interference, we'll say noise here. What a repeater does is before the signal, and remember we have 1 and 0, so it's easy to pick out the signal as long as it's stronger than the noise. Then we repeat the signal, we don't amplify. If we amplified, we would amplify the noise also, wouldn't do us a whole lot of good. So a repeater picks out the signal before it gets below the noise level and brings it back up to the original signal strength so that we can do the same thing again. So network adapters, repeaters, hubs, modems, and fiber media converters are all things that we're going to find at the physical layer of the OSI model. The data link layer provides node-to-node data transfer. Boy, that's a mess there, huh? Provides node-to-node data transfer, a link between get the wrong pen there. A link between two directly connected nodes. It detects and possibly corrects errors that may occur, and possibly corrects. And you're going to say this is the first place that we're going to have any correction. Typically not a whole lot of correction is there. It may detect an error and reject the frame, and that's going to be what we're going to title these things. This layer is going to be a frame. That may occur in the physical layer. Defines a protocol to establish and terminate a connection between two physically connected devices. Physically connected devices is the key here. So this is going to be a physical connection. It also defines the protocol for flow between the two of them. So physically connected means that they're going to be connected to the same switch or hub, for instance. Two devices are going to be a physical connection here. I drew my switch the wrong way, didn't I? A physical connection between these two. Let me see if I can do a better job of that. Let's say we have a switch here, and we have our ports here, and we have I can't draw a computer, by the way. Computer here and a computer here. That's going to be a physical connection. We have a very bent screen on this one. So connects these things. They operate at layer 2. And it's going to be the data layer. It uses the media access control layer, the MAC layer, which is also going to use a MAC address, which is going to be a 48-bit hexadecimal number. If you want to see it on your computer, you can do an ipconfig/all if you have a Windows machine, and you will see the MAC address in there. So it's a 48-bit hexadecimal address. The first half represents the manufacturer. The second half represents the a serialized connection or serialized device. So in these things, the MAC layer is responsible for controlling how devices on the network gain access to the media and have permission to transmit. What we do, and we'll go back to our, I wanted to get the MAC address in there, but the media access control, because we do use these things. And this is how a device determines if the data is actually to its MAC address, not to its IP address. IP addresses are going to be at the next layer. So what we're going to do here is we use a process called CSMA. CD. Carrier sense multiple access collision detection. Carrier sense, we're going to have a frequency here that is a carrier signal, just like you have with any other signal you're going to modulate. So what this device does is it listens to the wire to see if anybody else is broadcasting, transmitting. If they're not, it's going to send its signal. So we're going to, we'll change color here, we're going to send our signal out onto the wire. And then we're going to go from here to here. MAC address will tell which of these devices to accept the transmission. Carrier sense, multiple access, everybody's connected. Collision detection. After we send our data, we're going to listen to see if somebody else transmits at the same time, which hopefully we won't, and we have a collision. If we have a collision, we go into a random back off. So I'm going to do a random back off and start the whole process over again. And you get a collision message from the devices that detect those collisions, so that you know to start over that the data didn't get delivered, it got corrupted en route. So the data link layer, the LLC, the logical link control for identifying and encapsulating network layer protocols and controls error checking and frame synchronization. What that's saying is that if it comes in and it sees an IPv4 packet, it's going to send it up to the next layer, which is going to be the network layer, to the IPv4 portion of it. If it detects an IPv6 signal, it'll send it to the IPv6 portion of it. A MAC and LLC of 802.2 networks, 802.3 Ethernet, 11 of Wi-Fi, 15.4.15.4 Zigbee operate at the data link layer. Point-to-point protocol is a data link layer protocol that can operate in several different physical layers. Synchronous and asynchronous. Synchronous is always online, your cable modem. Asynchronous, on demand, which would be something like a dial-up connection when we would do one of those. I'll do one more. We're at 22 minutes, but let's do the network layer. The transport layer gets to be a little bit more involved with this. I'm going to try a different color ink here. So the network layer responsible for addressing data packets, routing the packets from source to destination through the network, and ensuring data delivery. We're going to get into this ensuring data delivery in great detail at the transport layer. The network layer is where the IP address is. And IP addresses change. So IPv4 192.168.3.1 would be what it would look like, and IPv6 is going to be a hexadecimal number, 128 bits, 128 binary bit address, where this one is a 32-bit. So you can get an idea, we'll talk about that as we get into it, you can get an idea of how much bigger the IPv6 address space is. Controlling congestion on the network by making proper routing decisions. Again, let me get rid of some of this. So if we had, and I usually use a circle for routers, if we have a bunch of routers here, and we're going to have multiple paths to get from one location to the other. It would be responsible for controlling the congestion on the network by making the proper routing decisions, sending it to maybe the most efficient, or at least to the correct location or the correct interface to get from point A to point B. And here we see we have multiple paths. We're going to have different costs, different metrics that are going to allow the system to make those decisions. We'll get into what the metrics look like as we go through the course. Protocols for interconnecting two or more similar networks, IP networks, and those are the ones that we have today. You may see in your readings IPX. IPX is an older NetWare protocol. It was proprietary. It's not really used anymore. The local addressing is IP. And packet forwarding is when we use the route table, and we're going to look at all these things as we go in. The route table is going to tell the system where to forward the packet, what interface to send it out of in order to get to its ultimate destination. Path determination, choose the best route. This could be, we could have on-the-fly intelligent switching is what it's called, that we report congestion and the cost changes as packets come in, and then we will pick a different route out. Otherwise, we're going to pick whatever is reported. Actually, we're always going to pick whatever is reported from all these other guys to allow us to determine the best path based upon the metrics of the device. So at this point, we're at what, 25 minutes, and I told you I was going to try to keep them even shorter than that. I'm going to stop here, and then we'll continue with the networking models in the next module. Hope to see you there.